Hey, grade 10. So in this lesson, we're going to go over cosine law, and this is the last complete lesson that we have in Unit 5. So I say complete because technically there is another lesson that we go through, which is 3D problems, but I think I mentioned this already. It will not be on your unit test, but it will come up in the culminating. And the reason we didn't cover it on the test, just because it's not necessarily hard, it's just mainly looking at word problems. And there's really not much of a lesson per se, because it's more about you practicing with different types of problems that are more complex. So the last full lesson, like I said, is cosine law. Once you have sine law, cosine law, primary trig ratios, and Pythagorean theorem under your belt, you can basically solve any sort of trigonometric problem. Okay. So what we're looking at here is solving problems that involve oblique triangles using cosine law. So what we know so far, so we know that the primary trig ratio, SOHCAHTOA, can be used for right triangles. And Pythagorean theorem, I'm going to bring this up. We can still use it, but unfortunately, the Pythagorean theorem is very limited. We can only use it to find sides. It doesn't actually help us find angles. So that's why when you learned about the Pythagorean theorem in elementary school, you were a little bit limited. You could only find sides, not missing angles. Sine law, then we learned about, we can then use to find different sides or angles in an oblique triangle. But again, sine law also is a bit limited because we need to at least know one pair of corresponding angle and side. And plus you need to know the corresponding side or the angle of the unknown side or angle that you want to find. So you're a bit limited because you kind of need at least one pair of angle side, and you need to kind of half know either what the angle of the side that you want or the side of the angle that you are looking for. So if any of these cases above don't work, so if you look at this and you said, okay, I tried SOHCAHTOA, it's not a right triangle, so I can't do that. I tried sine law, but I don't have a corresponding angle and side that works, then you can try cosine law. So cosine law is basically kind of your last alternative, right? And you're going to notice that cosine law very much resembles Pythagorean theorem, which kind of helps a little bit. And to be honest, and this is more of a little extra note here, Pythagorean theorem is basically almost a special case of the cosine law, because when we look at the cosine law, we actually will look at how we consider the cosine of an angle. I don't want to go into too much detail, but essentially we notice that the cosine of 90 degrees would actually be, in that case, it would be 0. And because of that, you actually simplify your cosine law into c squared is equal to a squared plus b squared. So again, just letting you know, it does somewhat resemble Pythagorean theorem, but it's obviously more complex. So when do you use cosine law? Luckily, there's the cases that you have to, there's really only 2 cases you're looking at, and it's pretty easy to remember. Unlike sine law, where there's an ambiguous case or more different scenarios to consider, cosine law is pretty self-explanatory. You don't have an ambiguous cosine law case, which is really great. So cosine law, you either use it if you know 2 of the sides and the contained angle. So what I mean by contained angle is you have an angle that is between the 2 sides that you know. So you have 2 sides and then an angle right between them, or if you know all 3 sides. So pretty simple to know the cases. Like I said, sine law, much more complex. Cosine law, it's pretty easy to remember the cases. Basically, if you know 2 sides and the contained angle, or you know all 3 sides, you can use cosine law. So we use cosine law basically when there are no pairs corresponding side and angle. And you can even look here. In this first triangle, we have a side, but not a corresponding angle, right? So not there. We have another side, but no corresponding angle. And then we have an angle, but no corresponding side. So we have no pairs of corresponding angle and sides that we know. And in this case, we have 3 sides, but no angles. So obviously there's no corresponding angle and side. So for cosine law, what we do is we actually first identify the angle, the corresponding angle and side that are, I want to call them, there's not a special name for it, but I always call them like the special angle and the special side length you're looking at, right? It's not a formal name. It's just what I like to call it, kind of like the Aussie method. It's just what I like to call this. I look for the special angle and the special side in cosine law. So what I mean by special angle and special side is that it's either going to be the side length that you're looking for, if the side length is missing, or the angle you're looking for if the angle is missing. And you want to make sure that the angle that you're missing and the side length that you're missing, they correspond with each other, right? So you want to make sure that the angle that you're missing either goes in is labeled as capital C, or you label lowercase c for the side length that you're missing. So really important there. Little c represents the side opposite of the angle that you're looking for, or the angle C that we already know, right? So it's either going to be opposite of the side C that you're trying to find, or angle C that you already know. So that is how we pair them off. And then, just like Pythagorean theorem, the A and the B don't actually matter which one I label which. So I can actually switch them around. So the two remaining sides, I can actually label one of them B and the other one A, or vice versa, right? It doesn't really change the answer at all. So just like Pythagorean theorem kind of forces you to label the hypotenuse first, and then the other two sides can alternate, cosine law is very much similar. We need to make sure that we label side C as little c as a side we either know or want to know. And it's also the one that corresponds to angle C, which we also might want to know. So it's either side C that we want to know, or angle C, capital C, that we want to know, right? So we either want to know big angle C or little side length C, right? But either way, they have to correspond with each other. We don't use, so I just want to make sure that you understand this. We don't have to use side C as our main one. You could actually use different variables. That's fine as long as they match up with each other. So for example, there's different variations of cosine law, and I hope this doesn't throw you off. For example, I could, instead of using C, you will actually sometimes notice in the book, they might use something different. They might use A squared is equal to B squared plus C squared minus 2BC cos A. So notice that this is the exact same formula. The only difference is that I still have to make sure that the side A matches up with angle A. So basically the side at the very beginning of the formula, and again, this is going to be little a, has to match up with the angle at the end of the formula, which is big A. Likewise, I could rewrite this as little b squared is equal to a squared plus c squared minus 2ac cos b. And again, this is capital B to represent the angle. So remember we talked about this, lowercase always represents the side length, and uppercase represents the angle. So hopefully that makes sense so far, right? So we want to make sure that the side length at the very beginning of the formula matches up with the angle at the end of the formula, right? And again, those, we can switch the variables. We can make them either big C, little c, big A, little a, or big C, B, little c, little b. So let's look at an example when we're trying to find the side length C. So this one's a little bit easier because I purposely labeled angle C as the one we know, and side length C, little c, as a side length we're trying to find. But in the other examples, I won't necessarily label them for you, so you have to do the labeling first. So what we notice first is that the side length C is the one we're looking for there, which is across from 43 degrees. So we first realize that angle C, sorry, angle, I can label the other two sides, 7 and 5, as either A or B. So I'm going to call this one A, and I can call this one B. I could also switch this around. I can make this A and make this one B, just like I do in Pythagorean theorem, right? The two legs, you can switch them around, but the hypotenuse has to be C. So if I decide that this is going to be A, just for simplicity's sake, I'm going to make this A and this one B. Then I know that this angle for angle C has to be 43 degrees, and little c is the side length that we don't know. And again, if you don't know something in math, give it a letter, right? And in this case, let's make it simple. Let's just use the letter that's given to us, little c. And again, make sure, this is really important, you need to make sure that the angles correspond with each other, right? So the angle C corresponds with the side length C that is directly across from it, which we're actually trying to find. So when we set this up, we make sure that the side length C right here matches up directly with the angle C right there. So that means that I'm going to replace the C right here in the formula with C, which we're trying to find out. And I replace the big capital C with angle 43 degrees that pairs up with the side length C that we're trying to solve for. Does that make sense so far? Hopefully that's kind of clear. So we make sure that the side length that we're looking for in this equation, using this formula, matches up with the angle that we already know, the corresponding angle that we already know, which is 43 degrees. And as I mentioned already, A and B can switch, so I can really switch the order around there, but I'll just continue it on. So I have 7 squared plus 5 squared minus 2 times 7 times 5 times the cosine of 43 degrees. What's my next step here? Well, now that I've followed this through, it's just a matter of simplifying this expression. So I have 7 squared, 5 squared minus 2 times 7 times 5. I need to figure out what 2 times 7 times 5 is first. So I know that 2 times 7 times 5 is 70 degrees, 70. And notice that I do not make the mistake of multiplying it directly by 43. That's not what we're doing. This is separate, right? So I am going to find out what 2 times 7 times 5 is. That's 7. So that's 70 there. And what I'm going to do next, and again, be really careful with this. A lot of students make this mistake. They will look at this and automatically, I don't know what it is about your eyes deceive you. It's so tempting for some reason to want to subtract this. Are we subtracting that? No, right? Going back to beta maths, guys, do not forget beta maths. You learned it in elementary school, but I cannot emphasize this enough. It is so important. You want to make that you add first, and then you can add these separately here. But what you want to do before anything else, before subtracting off the 70 times cosine of 43, you want to make sure that you actually multiply 70 times the cosine of 43 degrees. So you want to multiply first, and then you want to carry out the addition and subtraction. Now, keep in mind that 49 plus 25, that's why I brought that up. I can actually add these, and it's not technically breaking a rule, but I cannot start subtracting out the 70. That's not how that works. I have to multiply 70 by the cosine of 43 degrees. So find out what the cosine of 43 degrees is, and then multiply it by 70. So let's grab a calculator. I just want to go through this with you. So 43, we find the cosine of this. That is then multiplied by 70. And that ends up giving us 51.19. So now I have 51.19. Oops. And again, when you get more comfortable with this, you don't, like I said, you could add 49 plus 25, and that doesn't break a rule. And then as long as you're doing this separately, right, you're not doing it together. But if you want to take it step by step, you definitely can. So you could multiply first, then you add, and then you subtract. So we end up getting 51.19. This is this answer right here, this product. So now we look at this next step and say, okay, well, now I can add 49 plus 25 is 74. And now that I've added, I can then subtract, which is the next operation. So I have 74 minus 51.19, and that ends up giving me 22.81. And we're almost done here. Our semi-last step is to simply take the square root on both sides. And again, we take the square root of both sides to isolate for C on its own, just like we did with Pythagorean Theorem. And this ends up giving us 4.8 centimeters. Now notice that I only have a positive answer. Why don't I have to consider the negative answer? Again, look at the context. What are we measuring? We're measuring a side length. Can length be negative? No. So because of that, you know that's only going to be positive. So it's only 4.8 centimeters. So your missing side length there is 4.8 centimeters. So we are given this triangle where we have x 28, 22, and the contained angle is 97 degrees. So first of all, since the labels are not given to you, then you need to label the angles and the sides as you see best. Well, first thing I realized is that the x right here has to correspond with the 97 degrees that we already know. And luckily, the side that we're looking for, the side length we're looking for, corresponds with the angle we already know, the contained angle. So I'm going to call this big C because it's the angle where I'm looking for, the angle that I know or the angle that I'm looking for. But in this case, it's the angle that I know. And little c will be the side length that corresponds to that angle that I know, which is 97 degrees. So I know that big C is 97, little c is x, which I'm looking for. And A and B, I already mentioned this, A and B can be whatever, so the two side lengths left over, this can be A, this can be B, or I can switch it around. I can make this B, and I can make this one A. Doesn't make a difference at all. I'm going to keep it with what I have here. That A is 22 and B is 28. Again, it's just like Pythagorean theorem, right? You can switch around the order there. So then you end up with, and I'm going to erase this because this is actually the new order that I have there. So I have, I end up getting big C, little a is 22, little b is 28. So I sub that into my formula. And again, the two, so notice that the variables that we use, it doesn't actually matter in this case, but we need to make sure the most important thing, that angle C matches 97 degrees, the angle that we know matches up with the side length that we're looking for, right? That's extremely important. They have to match up. So I make sure that 97 degrees goes into big C right there, and X, the side length that I'm looking for, the missing one, it goes into C, little c. So now that I have that, like I said, A and B can switch around, doesn't make a difference. I simply plug everything into my formula. So little c is still gonna be little c. So I have c squared is equal to 28 times the cosine of 97 degrees. So I go through the steps here, little by little, right? So I'm gonna find out what 2 times 22 times 28 is. 2 times 22 times 28 is 1,232. And I'm gonna simply multiply that by the cosine of 97 degrees. Again, be careful with this. We find a cosine of 97 degrees, and then you multiply by 1,232. So we want to be really careful with this. And I want to kind of bring up a little technicality or a little strange occurrence here. So when we find the cosine of 97 degrees, I'm not sure if anyone can guess what's going to happen. If you look at your CAS rule, you're going to notice that because 97 degrees is in the second quadrant, the cosine ratio will be negative. So notice that I actually end up with a negative answer. And for some reason, this throws a lot of people off, the fact that it's negative. It kind of confuses people because they don't really know what to do with it. Just continue with it, right? Again, remember your order operations, and remember what to do with integers. So because it's negative, don't worry about it. We still follow the same rules as before. We're simply going to multiply by 1,232. This ends up giving me negative 150.14. So this answer right here, so I want to make sure it's clear to everyone. This answer right here, when I multiply, this answer ends up giving me negative 150.42. But because I'm subtracting a negative, I actually end up adding 150.14. So that's why I end up getting a positive answer. And that's why it ends up looking like a positive answer, right? Because I'm subtracting a negative answer, and I'm subtracting a negative product, which means I'm really just adding 150.14. So this is not a typo. A lot of people sometimes will ask me, did I make a mistake there? I know I make lots of mistakes in the lessons. You've probably seen that, but this is actually one of those cases. It's not a mistake. I promise you it's not. It was very much intentional, right? So you want to make sure that you note that difference, that actually we're going to be adding that product. And the reason for that is because you're subtracting a negative, which is getting 1,268. And where did I get that from? That's just from 484 plus 784. That gives me 1,268. I add 150.14. This ends up giving me 1,418.14. And my last step here, I simply take the square root on both sides. And when I take the square root, again, I only consider the positive answer because it's a real life situation. And I get 37.7 centimeters. And that's my side length that's missing. So you always look at the answer and you check, does it actually make sense? Well, I can tell you right now, it does make logical sense because on this picture, so it would make sense that the largest angle would have a corresponding side that is larger than the other two sides. So if you got an answer that was less than 22 or less than 28, you know you're doing something wrong. So the fact that the answer is larger than 22 and 28 means you're doing this correctly. All right, let's look at the last example here. So finding an angle, how do you find an angle with cosine law? So in this example, we notice that 7 is opposite of the unknown angle. So because 7 is directly opposite of the missing angle, because 7 is directly opposite of the missing angle, we know that this missing angle is special. We're going to label this as big C in the cosine law. And its corresponding side is going to be little c, right? Again, remember that C is always going to be, capital C is always going to be the angle you're looking for or the angle you know, and little c is going to be its corresponding side. So in this case, 7 is a little c, the corresponding side, and big C is the angle that we are looking for. So we have 5 as one of the two other lengths that are not special, and 8 is one of the two other lengths that is not special. And again, the A and B can switch. I can make this one B and I can make this one A. It doesn't make a difference. What I know into the cosine law. So I have 7 squared. Again, 7 squared is coming from the fact that little c is the side that corresponds with the angle that we're looking for, and big C corresponds with the angle that we're also looking for, which is P in this case. We label this P. So we simply replace little c with 7 and big C with P, because that's angle P is what we're looking for here. So now we have 7 squared is equal to 5 squared plus 8 squared minus 2 times 5 times 8 times cosine of P. Again, 2ab right here is just replaced with 2 times whatever the a value is, which is 5, times whatever the b value is, which is 8. And again, I could switch this around and you're going to notice you don't actually get a different answer at all. That's what, so again, I say quote unquote special. It doesn't actually have a name. But just like in Pythagorean theorem, you had to label your hypotenuse and the other two legs. Didn't really matter which one you labeled, A or B. It's the same thing with this. You always want to label your special angle on your special side. And then the other two sides you can label as A or B. It doesn't really matter. So when I go through the steps, I know I first have to multiply 2 times 5 times 8. 2 times 5 times 8 is 2 times 5, which is 10 times 8, which is 80. So I end up getting 25 plus equal to 49. So this question's tough. Again, your eyes playing mind tricks with you, especially this one I find. When people look at this, once again, I don't know what it is, but it's very tempting to want to subtract these numbers. I don't know what it is. It's just because they're near each other. It's just the proximity. It just is tempting. I get it. You're tempted to do that, but please don't do that because that's not correct. Again, we know that we have to use BEDMAS, so we still use BEDMAS even if it's an equation. So we look at this and say, well, 25 plus 64, I'm just going to add them up. I know that this ends up giving me 89, and I put a little arrow there, by the way, just to make sure you're not making the mistake. So do not make the mistake of subtracting these. Again, the reason I cannot subtract this, sorry, simply add and then subtract the 80 is because it's actually not 80. So that's actually a totally different expression, right? This is a variable here that we have. So think about it this way. I'm going to give you a different example. You might understand this a bit more. If I give you something like this, 5 plus 4 plus 3x. Remember when we talked about like terms? So we know that according to like terms, you can add the two numbers here, 5 plus 4, which gives us 9. But you cannot just add the 3 there, right? You cannot make the mistake of saying, oh, 5 plus 4 plus 3, that gives me 12 or 12x. You know that doesn't make any sense, right? You know you're not allowed to do that because these two are like terms, and the 3x is not a like term with 4 and 5, right? Because it's not a number. It has a variable x there. So it's the same idea here. You just don't think about it this way. But really, the 80 is actually a coefficient of this variable. You want to think of it that way, right? The cosine of p. It's a trig ratio that we have. And unfortunately, there's really not much you can do here, but leave that alone. This 80 minus times cosine of p is totally separated, right? And that's why I put that little lightning bolt. So you kind of remember, you got to be really careful with this, right? I want to make sure you understand this. This is separate from the other two numbers here and the other number on the other side, right? So you want to figure out what 25 plus 64 is first. Just add those two. Do not subtract off the 80, okay? They're going to hear that warning. The fact that I put the lightning bolt here means don't forget, okay? You're not going to subtract. You're not just going to add and subtract the 80. You got to figure, you have to do this separately. So take 25 plus 64, that gives you 89, minus 80 times the cosine of p. And then what you're going to do next is you're simply going to subtract off 89 from both sides. Subtract off 89 from both sides. That ends up giving you 49 minus 89. That gives you negative times the cosine of p. What do we do next? Well, now we notice that we can divide both sides by negative 80. And again, I'm dividing by negative 80 so that I can get cosine of p by itself. So again, if you're getting confused by this, I'll go back to an easier example up here. So back to that last example that we did, I'm going to add more to it. If I give you something like 10 is equal to 5 plus 4 plus 3x, and I ask you to solve for x. Well, first I add up only the numbers, so I get 9, and that's equal to, and on the other side I have 10 plus 3x. What do I do next? I have to bring the 9 over, so then you end up getting 10 minus 9 is equal to 3x, and we know that 10 minus 9 is 1, so 1 is equal to 3x, and then we divide by 3 to get x by itself. Well, that's essentially what we're doing here. We're simply dividing by the coefficient in front of cosine of p. So we divide by negative 80 on both sides. And when we divide by negative 80 on both sides, this actually simplifies to negative 40 divided by negative 80, which is 1/2, because the negative divided by negative is 1/2. And then we end up with something a little bit easier now. We end up with 1/2 is equal to the cosine of p. Now we have the cosine of p on its own, but we are still not fully on its, the p is still not fully on its own. We know that to get p by itself, to completely isolate for it, we had to find the cosine inverse of 1/2, or you could really figure this out using your special triangles, right? Going back to your special triangles, and again, you need to know this for your test anyway, so I hope you remember this. You know that, let me erase this here. If I tell you that the cosine ratio is 1/2, that means the adjacent side is 1, the hypotenuse is 2. So if we draw a special triangle here, so we have an adjacent side of 1, and adjacent side of 1, and a hypotenuse is 2. So that would mean by default that the opposite side would be square root of 3. So we notice that this is a 30, 60, 90 triangle. So what is directly across from square root of 3? It has to be 60 degrees. So I know for a fact that this angle has to be 60 degrees, but of course you could use a calculator just to verify it, and then you'll see that the answer is 60 degrees there. So that is angle P. So one last little warning here, when you're finding the angle using inverse, sine inverse or cosine inverse, you may actually sometimes notice that there's an error, and there's a reason for that. It's because you're not always able to find the sine or cosine inverse of ratios. And you actually specifically cannot find the sine or cosine inverse of ratios. Sorry, you cannot find the sine or cosine inverse of ratios that are greater than 1 or less than 1. That's what I meant to say. Sorry, guys, it's a late night. I may make some mistakes along the way. So essentially what we notice is that when you're finding the sine inverse, cosine inverse, sometimes you don't get an answer, right? So for example, I'll show you my calculator here. If I take the sine inverse, let's say you do the work here, and again, I warn you about this just because if you ever notice that there's an error, you don't look at your calculator and think something's wrong with my calculator. It could be something wrong with your calculator, but very likely it's that you made a mistake here, and it's actually not even a possibility. So if I find the sine inverse of 2.3, I get invalid input. What does that mean? So the reason we're not allowed to do that is, again, going back to what what sine ratio and the cosine ratio tell us. The sine ratio is opposite of hypotenuse. The cosine ratio compares the adjacent side with the hypotenuse side. What do we know about the hypotenuse of a right triangle? Well, we know that in a right triangle, the hypotenuse is very special because it is always the largest side of all the triangles. So if this is my angle right here, my reference angle, this is my opposite side, here's my adjacent side, I can tell you right now that my opposite side will always be, my hypotenuse will always be greater than the opposite side, regardless of what the reference angle is, and will definitely always be greater than the adjacent side as well. So because of that, because we're always dividing a smaller number by a larger number, we know that that ratio will always be less than, one. Less than 1 and greater than -1. So we know that it has to be between -1 and +1, the sine ratio and the cosine ratio. Again, we're going to talk more about this in Unit 6 when we look at the graphs of the sine function and the cosine function. But I just want to let you know that if you ever see an error in your calculator, don't freak out. It means that, if anything, it's a little warning to you that maybe you did something wrong, so you maybe have to go back to your calculations. Again, I'm not going to put something like this on a test, but I really do want you to see the sine function, the cosine function, what they look like. And specifically, we're going to be looking at its range. And we're going to see here that it's going to be slightly limited. And when you get to grade 12 math, you're going to also learn about the graphs of different functions, and we're going to see what they also look like as well, which is really quite interesting. So we're going to be looking at some of the limitations when we find the cosine inverse and sine inverse as well. So I hope this makes sense. I know this was a long lesson, like I said, well, shorter than the other ones, but still a lot of new content. And that is basically it. That's, again, just a little warning about your calculators there. So good luck with the test. Hopefully it all goes well. And again, Unit 5, I know it's long, but we are almost done.